Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about a very popular continuous random variable. We will talk about the continuous uniform random variable. Let me tell you what's the plan, okay? What I would like to do with you in this video. First, we are going to see what's the expression that defines the probability density function PDF of a continuous uniform random variable. Okay? Then we are going to find a formula for the expected value of this kind of random variable. And finally, we will do an example where a continuous uniform random variable is involved. Okay, so that's a plan. Okay, first let me show you that definition I mentioned. Right? So we have two numbers, theta 1, theta 2. Theta 2 is greater than theta 1, and then they define an interval. So if a random variable, right, has a PDF, a density function that looks like this, 1 over theta 2 minus theta 1, right, for values between theta 1 and theta 2 and 0 elsewhere, then we say that y has a continuous uniform probability distribution, or we say that y is a continuous uniform random variable. Make sense? Now think about it. These two numbers are constants, right? So once you do 1 minus this is just a number. So what we're saying is the graph of this guy, f at y, is a constant between theta 1 and theta 2. If it's a constant, that means that we have a horizontal line between theta 1 and theta 2. That's what the graphical representation of the PDF will look like for a continuous uniform random variable. Make sense? Okay. So now let's talk about the expected value and variance for that random variable. First, let me remind you that the expected value is just a numerical summary of center. Okay, that gives you an idea of where the center of the distribution is. Okay, and also let me remind you that the variance is a measure of spread of variability, okay, with respect to that center, with respect to the mean of the random variable. Okay, so according to this theorem, this result, if you have a continuous uniform random variable, its expected value is given by that formula, theta 1 plus theta 2 divided by 2. Okay, we are going to show that this is true, that that formula works to find the expected value. And if you want to derive the one for the variance, well, then you can do it later on your own. It's not going to be that hard, but the only one that we're going to be doing together here is the one for the expected value. Let's find it. So we want the expected value of a continuous uniform random variable. Okay. So expected value of y. Expected value of y. First, as usual, if we want to find the expected value, it's a good idea to start with the definition. So by definition, the expected value of a continuous random variable, right, in general, it's going to look something like this. The integral from negative infinity to infinity of y times the PDF, right? That's just by definition. Okay, so now in this specific case, what we said is that the PDF will be 1 over theta 2 minus theta 1 between theta 1 and theta 2, and it's going to be 0 elsewhere. Remember? Let me go back to the slide where we have PDF, right? 1 over theta 2 minus theta 1 in the interval theta 1 to theta 2, 0 elsewhere. So what we have here is this: between negative infinity and theta, let me see which one is the left end, theta 1, okay, and theta 1, we have 0. You guys agree? We have nothing there. Plus, between theta 1 and theta 2, we are going to have that line we talked about. Remember that horizontal line we talked about? 1 divided by theta 2 minus theta 1. Plus between theta 2 and infinity, we will have 0. Make sense? So the only one that matters is the second integral. That is the only one that is going to be different from 0. So let me copy paste that guy. Now remember, theta 2 and theta 1 are constants. So theta 2 minus theta 1 is going to be a constant. 1 over that constant is going to be a constant. So let me just factor that out. Now, this is the integral of y with respect to y. That is going to be just y squared divided by 2. And we have to evaluate at theta 2 minus the evaluation at theta 1. So let me copy paste this and write that down. So we have this times, we said we are going to have y squared divided by 2, and we have to evaluate theta 2, right? So we will have theta 2 squared minus same thing, y squared divided by 2, but now evaluated at theta 1. So let me copy paste this. There we are. Make sense? Okay, now note we have a common denominator here. Let me rewrite this in a nicer form. So the first factor here in this multiplication I will leave unchanged, but the second one is the one that I want to write in a nicer form. Okay, so let me write it down like this. As you can see, 2 would be, our common denominator. We could rewrite this like that, theta 2 square minus theta 1 square, both of them divided by 2, right? Now, note that theta 2 square minus theta 1 square is the same as theta 2 minus theta 1 times theta 2 plus theta 1. So that's what I'm going to be doing here. And I'm going to be writing that down like this. I just remove this guy here. Well, let me do it like this. It's going to be, as we said, theta 2 square minus theta 1 square is the same as theta 2 minus theta 1 times theta 2 plus theta 1, right? We know that from our courses in algebra, right? But now these guys cancel out, and what we are left off with is that beautiful expression, theta 2 plus theta 1 divided by 2. That would be the expected value of y if y has a continuous uniform distribution. Make sense? And I believe that's what you will have here. Okay, so if you want, you can try and find the variance of y. It's not going to be that hard. Okay, give it a shot. It's good practice. Okay, so now we said at the beginning that we were also be doing an exercise together. Let's do that exercise together. So take a look at it, read it. Got it? Make sense? So in this case, the random variable of interest is the flight time from Cincy to Tampa. Okay? Okay. So it makes sense that we are considering a continuous random variable, right? Time could be considered to be continuous, right? If we could measure time with infinite accuracy. Okay, so first they tell us for this example that they want us to show the graph of the PDF, the probability density function. Okay, so let's read the problem carefully, and here they tell us that they are assuming that a good probabilistic mathematical model for the flight time from Cincy to Tampa is a uniform, continuous uniform random variable that goes from 2 hours to 2 hours and 20 minutes. Okay, so to make that graph, how about we go back to the definition of continuous, a uniform continuous random variable. It looks like this, right? So they said that it's going to be that flight time is going to be assumed to be uniformly distributed from 2 hours to 2 hours and 20 minutes. Okay, so those are the two parameters, right? The left and right end of the interval. So let's do that exercise. So for that example, theta 1, the left end, 2 hours, right? So 2 hours, but how about we express that in terms of minutes? So 120 minutes, that's our theta 1. Theta 2 would be the right end of our interval, and it's assumed to be 2 hours and 20 minutes. So 2 hours, 20 minutes, that's 140 minutes, right? So using that expression for our PDF, so case 1, if let's use I don't know, let's use x, right, for the random variable of interest. So if x is between 120 and 140 minutes, according to that expression, it must be 1 over theta 2 minus theta 1. So it would be 140 minus 120, right? 1 over 140 minus 120. Okay, f at x, because I'm using x for this one, f at x equals 1 over 140 minus 120, that's the same as 1 over 20, and 1 over 20 is the same as 0.05. Yeah, okay. Or if you like that better, 0.05. Okay, and the other case is case number 2. F at x will be 0 elsewhere. Oops, sorry. Otherwise. Okay? Are we good? Okay, so clearly, again, this would be a flat line, horizontal line with height 1 over 20 between 120 and 140 40. Okay, makes sense? So now let me show you a graphical representation of that guy. I prepared that for you here, right? Between 120 and 140 we have a flat line, a horizontal line at 0.05. Make sense? Okay, so that's the graph of the PDF, and it's just another way of expressing a probability density function. It's a graphical way of expressing PDF. Okay, now part B. Let me go back to the problem here. We would like to find the probability that the flight will be no more than 5 minutes late. Okay, so first we have to state that probability in terms of the random variable x that we defined here, right, where x represents flight time from Cincinnati to Tampa. So let's say that the random variable of interest x represents flight time from Cincinnati to Tampa. Okay, so let's try and set up the problem that we want from part B. Okay, again, what's the probability that the flight will be no more than 5 minutes late? Okay, so according to these guys, to Delta Airlines, they claim that they take 2 hours and 5 minutes to go from Cincy to Tampa. Okay, so they are going to be late if they take a bit more than that. So more than 2 hours and 5 minutes, meaning more than 125 minutes, but we want to be no more than 5 minutes late, up to 5 minutes late. So that would be, we want the probability of x being greater than 125 and less than or equal to 130 minutes. Make sense? That's a probability of the event that we want. Probability that x is between 125 and less than or equal to 130. Okay. Now we know, right, that if we were dealing with discrete random variable, it would be the sum of the values that fall between these two guys, right? But now we have a continuous random variable, so instead of doing sums, we do integrals. So now what we want is the integral from 125 to 130 of your PDF, right? And your PDF looks like this. I like fractions, so let me use a fraction here. PDF dy. Okay? Now that guy is just a constant, so we could factor it out. Let's factor it out. Now, the integral of dy, which is basically just a1, what we have here, is just y, right? Evaluated at 130 minus 125. So let's write that down. This happens to be the same as 130 minus 125 divided by 20. And that happens to be the same as 5 divided by 20. and that's the same as 1/4, right? 1/4, or 0.25, right? Okay, so that's the probability. Now let me show you something interesting, something that I prepared for you. As you know, right, the integral is the area underneath a curve, right? So in this case, when your curve, when your PDF looks like this, like a horizontal line, what you want is just the area of that rectangle. So base 5, height 1/20, and that's what we ended up with, right? 5 times 1/20, so 25%. That's a probability of that event. X, the flight time, being between 125 minutes up to 130 minutes. Okay, let's go back to the problem, and let's try and do the next part. So in this case, what we want is the probability that the flight will be more than 10 minutes late. Okay, so that would be the probability of being greater than 135, right? Part C. What we want now is probability of being more than 10 minutes late, right? Let me check. Yeah, more than 10. So that would be probability that X is, and it's more. So since it's more, would be this. Now, remember that in the case of a continuous random variable, even if I used greater or equal, that would yield the same result as just strictly greater than 130, because 1 point for a continuous random variable doesn't make a difference. Okay, we already discussed this in another video, but it is not bad to remember that. Okay, it's not going to hurt. Okay, so what we want, right, is that probability, but note that again is just the integral, right, from 130 up to infinity of the PDF. Let me write it down like that, and then I'm going to write down the integral, well, the only integral that is going to really matter, right? So that's what we want. You guys agree? From 130 to infinity of the PDF, that integral. But note that, oops, note that, as we said, we have two cases for this PDF. Between 120 and 140 we have that constant, and elsewhere we have 0, right? So from 130, oh, it's 10 minutes, right? So more than 10 minutes late should be 125 plus 10, it would be 135, right? Sorry about that. So from 135 to infinity of the PDF, and as I was saying, we know that we have two cases, so the PDF between 120 and 140 is going to be 1 over 20, but elsewhere is going to be 0. So what we want here is between 135 and 140, we're going to have 1 over 20, and then it's going to be 0 outside that interval. 1 over 20 plus, and then we have from 140 to infinity, we have 0. And I'm using x, right? So let me be consistent here with the notation. That's better. Yeah, let me be consistent. Let me change it here. That should be x. X. That's better. Okay. Very good. Okay. So anyway, that's going to be a nice, easy integral. We get to factor out 1 over 20. Right? And then it's just going to be 140 minus 135 divided by 20. We're going to end up again with 1/4, right? $120 times 140 minus 135, so it's going to be 5 divided by 20, $1/4, same as before. Okay, now let's do the other part, expected flight time, right? And now here, let me remind you what the graph looks like. Graph of the PDF. It looks like this, right? We know that the expected value is a measure of center. So the center of this guy seems to be 130, and we already have derived the formula for the expected value of a continuous uniform random variable, right? Remember, I think that what we said was that the expected value for a continuous uniform random variable was theta1 plus theta2 divided by 2, right? So in this case it would be 120 plus 140 divided by 2. So let's do that, right? So theta1 plus theta2 divided by 2. Remember that one, and let's apply it in this particular case for part D. Okay? Part D, the expected value of y theta1 plus theta2 divided by 2, so it would be 120 plus 140 divided by 2. So that's 260 divided by 2. And that happens to be 130. So our intuition was right, that the center of that graph is 130. That's expected value for a continuous uniform random variable, the center of that graph. Okay? Finally, just let me show you something. Remember that we did part B? We found a probability. The probability that the flight time is between 125 and 130 minutes, meaning no more than 5 minutes late. Okay, so let's try and redo that one using R. Okay, here we have R. So we are doing part B, right? First, we want an integral. We want the integral of 1 over 20 or 0.05, right, with respect to x, right? Now let me define it. Let me call it f at so a function of x, right? Now curly brackets 0.05 times x to the 0 power. X to the 0 power is the same as 1, right? So 0.05 times 1, 0.05 or 1 over 20. That's the function that I'm defining. Okay? It's a function of x, and that arrow there is telling R that we are assigning that function to the object called f. Okay? There we are. Now what we want, and I think we have used this function before, integrate f. The lower limit for that integral is 125, and the upper limit for that integral is 130. So 130 is the upper limit. Let's see what we get. 0.25. There we are. Nice, huh? Now just for fun, let's do part D. We know that by definition the expected value of a random variable is the integral from negative infinity. Oh, we don't have it here, but it's the integral from negative, oh come on, it's x here. It's the integral from negative infinity to infinity of x times the PDF of x, right? Let me write it down. By definition, the expected value of x equals integral from negative infinity to infinity of x f of x dx, right? Okay, now let's try and see if we can do that using R. So now I'm going to do this, x times f, okay? That's a new function, the product between x and the PDF we have already defined. It's a function of x, and between those curly brackets what we have is 0.05, that's the PDF, and let me do the x part. Okay? No problem, right? Okay. Now we want to integrate that new function that we called xf. The lower limit is from negative infinity to infinity, but between negative infinity and 120 we have 0, so that doesn't matter. But between 120 and 140 we will have that expression 1 over 20 times x, right? And then from 140 to infinity we have 0. So this is the part that we care about. That's expected value. Okay? So let's summarize. What we have done here today is we introduced a famous continuous random variable, the continuous uniform distribution. We derived a formula for the expected value, and then we worked on an example where we applied this distribution. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.